Okay, we continue. I was saying something. Yeah, that under low level programming language, yeah, we have machine language, also known as binary language, and we have assembly language. So what happens here, we are not going to study binary language because it's clear that you cannot write a program using just zeros and one and so on and so forth. So that's why we have another type of programming language, low level programming language, in fact. So these are just programming language close to the hardware part of the computer. So here what we are studying is what? Assembly language. And here also we are not really studying how to write assembly code, things like that. No. The only thing that a DC board requires from you is at least to master the structure of an instruction, the format of an instruction. So that instruction is for the assembly language instruction. Take note of that. So an assembly language in fact just a type of programming language made up of symbols and keywords called mnemonics. Yeah, they call it mnemonics. Yes, good. So this is what happens here. So example, if I write something like this, at maybe 4 5, this is an assembly instruction, and I think everybody can interpret this. Good. So here we are just calling an operation at it uses the values 4 and 5, add them and store the result and so on and so forth. So the idea of this part just to study instruction like this is all the format of instruction, and generally you have so many types of instruction. Now what you need to understand is that generally we have different type of processors, and each type of processors have what we call set of instruction they can process, or let me just say set of operations they can process. So generally here, but the most important one that you need to know is at least what add, for subtraction is sub, multiplication is small, maybe instruction to store something in the memory is store, instruction to load something from memory to a particular register is load. Take note of that. And how are we using them? It's very easy. This is the structure here, please. Generally the structure is destination source, meaning what? Example, if I write something like at, maybe this is R1 here, this is R2 here. Now R1 here is a register. Generally when they use R here means registers. So this means what? When I say this is destination here, this is source here, it's simply because this instruction simply means that you take the content of R1, you add it to the content of R2, and this result is being stored back into R1. So this is how we interpret when you see this type of thing. Please take note of that. Now for multiplication, addition, in fact the same thing. If I take now the case of store, what you're supposed to understand about the instruction store is that store in fact is helping us to take something from a register to a memory. And generally different type of processors have their instruction sets, because we call them instruction sets. Good. And different type of processors have their set of instructions. Now there are some processors where maybe store we have maybe here register this way, and maybe the memory now is this way. Like there are some processors where the memory is represented here at the first position, then the register is after. But that's why during the level of the DC we don't disturb students here. If you come and write store, you write your memory this side and you write register the other side, is no problem. But understand the meaning of store. The instruction store here simply means what? That takes something from register and store it where in the memory. Now the instruction load means what? Load now is the reverse. Load here means what? Take something from the memory. Remember that memory is being represented using this square bracket. Don't forget that, please. So load here means take something from memory and store where? In the register. And what I'm explaining here is very, very important, because there are questions that we are going to answer and we'll be manipulating this. So at least knowing the meaning of load store is clear. It's very easy and it's interesting. So generally when we talk about load and store, the first thing that I want you to retain is that here we are manipulating memory. Good. Now but when we are talking about the other operation like add, subtraction and so on and so forth, then there are some operation where it's only maybe register. Like here you see that the value that I want to add, they are stored in registers. You see, like you can also have something like this at A, B. In this case A and B here, they are not registered, but they are just address of memory location. So when I say when I say at A and B, it simply means for that at the memory location B, I take its content and add it to what is stored at the memory location A. Good. So just to tell you that in exam, generally for register we use R, and when we are just using maybe letters of the alphabet like that, they are just representing maybe address of memories, things like that. So you see that you can have an add operation also with what? With memories only. see. But for store, you never have store register or load register. No. Generally, if you want to move something from a register to another register or a memory to another memory, there's another operation here we call move like this. So move here is now to move. I can have something like that, R1, R2. Good. And what did I say? That the first part here, the destination, the second part is the source. So move R1, R3 means that you take the content of R2, you store it in R1. So these are just some of the instruction you need to know. It's all because when we talk about instruction sets, in fact, we have some architectures that have maybe 1000 instruction in the instruction set. So but for your level, just master these small things here, and it's all okay. Now we go to the next part. It's not all. So this is just the introduction. We continue. Let me just increase this. Okay. Now the next thing here is I want you to understand what we call instruction format. Good. Before going to the instruction format, you need to understand type of instruction. So you see, I have so many things to say here, so I'm trying to organize it. Okay, before we go there, let us talk about type of instruction. This one I want to mention it because even this June 24, 25 here, this first question they're asking that. Good. And the idea, I'm asking you to answer paper 1 question because paper 1 question also are based on chapters. Like when you answer this MCQ question, you always realize that the first 5, sometimes first 5 or first 4, something like that, they are always under computer architecture. Always. Go and see 25. It's so that now the setting changes in fact. But when you look recent here, like doing June 25, 24, you see it's under computer architecture. And type of instruction that I'll be mentioning here is something that I think under 2024 is going to help today. Now, type of instruction. So let me just take a red pen. Okay. Here, this is what we call zero address instruction. Zero address instruction. This is what we call, let me just leave space so that I'll be giving an example on the zero address instructions. Zero address instruction. There's one address instruction, there's 2 address instruction, and the last one here is 3 address instruction. So play the differences between them, they are very easy. Now before giving the difference, let me just take let me just explain what's an instruction format so that we will come there because it's related. So generally instruction format here simply represent the format of an instruction being interpreted by the CPU, or you say by your processor. And generally the basic structure of an instruction format is made up of 2 parts. The first part here is what we call the opcode. The second part is what we call the operand. Never forget this. The opcode and the operand. And you can ask in the exam to explain that. And opcode here, please, another name of opcode, the full name here is operation. This op here means operation code. Now, so the opcode simply represents an operation to be performed. For example, when I say something like at maybe 3.5, please, this at here is what we call the opcode in fact. So opcode are operations in fact that are to be performed on values. So this is what happens here. Now operand, what's an operand? So an operand simply represents the data on which an instruction will be performed. So when I'm saying here, like this example here, 3 and 4 here, they are operand. This is how we call them, they are operand. So this instruction at now is bit what the operation at is being performed on this operand 3 and 5. So have that in mind with examples like this, so that in the exam you can develop, you can write something there. As I'm always telling my students, no need to cram something, just understand and you can use your own words, you write this, no problem, no stress. Good. So this is what happened here. This is the basic structure. Take note because it's not the only field you can have here. Sometimes there are other fields that we add to this instruction format, and I'm coming to that. So yeah, I'm just explaining the basic format first. Now, so let us come back now to type of instruction. When we talk about type of instruction here, zero address instruction here simply means what? It simply means that an instruction is made up of one opcode. In fact, the opcode is always present. Take note of that. It's made up of one opcode, and the operand field is not precise explicitly. What's the meaning of that? Let me come back to that. Another name of this zero address is what we call the stack-based address instruction. Now, when they say that here one opcode is precise and zero operand is being precise, explicitly. It simply means what? That when you call maybe your instruction, you don't write something like that at full stop. You don't write anything. You don't precise any operand. Now, and how is this addition now going to manipulate values, things like that? That's why we call it stack based. Simply because in this case with zero address, what happens is when you call an instruction, this instruction automatically will use what we call the pop. I think everybody did here. Everybody here did data structure. You know this, what we call stack. A stack, in fact, is a data structure that uses the principle of what? Of LIFO, last in, first out. And it's exactly what this man is using. Generally, when you have a stack, you have, let us say you have element like this. Something like this. Let us say here is A, let us say here is B. And let us say this stack is called S. If I say maybe pop S, what happened? Pop S here simply means that the last element at the top is returned automatically. Are you getting the point? So, and it's the same thing that happened here. So when we call the instruction at, we don't need to precise the operand value here. No. Automatically he's going to pop the two last elements in fact of your stack and perform the addition operation. Meaning that when it says zero address, it simply means that we don't precise the operand, but the instruction knows where he is supposed to fetch his operand to perform his value. That's why we call it stack based. Take note of that. Paper one, I repeat again. You will see it there when you'll be answering it. Now, example, let me just take another example. Example, they can ask you to represent the instruction C equals to A plus B using zero address instruction. This is a simple question. They say represent the instruction C equals to A plus B in assembly language using zero address instruction. Yeah, this is how they can ask it. Represent this using zero address instruction in assembly language. It's all. To do the solution, what are you going to do here? Since you know that zero address is a stack base, so what happened here? Your first instruction will be what? You will say push A. Push A means that okay, in your stack A is here. Then you say what? Push B. Everybody know the instruction push. That's why I was saying that I hope everybody here did stack on the data structure. But I've defined nothing. It's easy as what I'm showing you. All. Now, push B. You push B. Now after doing this, now you just call your operation what? Add. This add here. Let me just use another pen. This add here. This add. This is here. Add. You just call the add. In fact, when you call add, what happened? Automatically the add will do the pop. Meaning he's going to pop A and B and do the sum. So the sum here will be what? A plus B. And after doing that, now he's going to push back the result automatically in the stack. Meaning he's going to push back this in fact. So now the top of the stack here, meaning that this is your new stack, and the top of the stack is having but A plus B. So after doing that, the next thing is what the result must be stored in C. So yeah, you're just going to say pop C. Pop C here simply means that C is taking what? Is taking A plus B. So this is the assembly code. So you're seeing that here, this is my operation here. No operand precise directly. Good. So before we go now to one address instruction, if everything is clear, leave a comment. So just say okay or a like. So let me confirm. Okay. Some people send like. Comment section, just type okay. If you're not understanding something, yes, I can just re-explain it. Comment section, just type okay. Right, yes, ask your question. We don't really have time, please, so be very fast and brief.
Sir.
Yes.
Sir, I'm not understanding how after pushing those elements in the stack, yes, how are they actually storing the not in the date variable C?
No, C.
Like, how can you repeat?
C is not stored. Remember that C here in fact is what? It's just a, like, let me just say it's a register or it's a memory location that must store what? The result of A plus B. So, okay, so yeah, when I'm doing pop C here simply means that okay, you know that pop means what? Remove the top element of the stack. And what is top element of the stack here is what? A plus B. That A plus B will store where now? In C. Are you getting it now?
Yes, sir.
Okay, so I'm happy by understanding it. Okay, so we go down to one address. So please never forget, especially this word that I'm saying stack base for zero address. Take note of that. Okay. Now, so we go to the next one address instruction. Now, at the level of one address instruction, and to summarize this thing, please, these numbers that you are seeing here simply represent the number of operand being precise. It's all. the opcode is always there, but the operand now, it depends. Now, the one address instruction is also known as accumulator base. Accumulator base. So when we talk already about accumulator, please just know it's one address. So yeah, this is just a type of instruction where we precise one opcode and what and one operand. It's what you say. When you define two address, the same thing. A type of instruction where we precise one opcode and two operand value. Three address, a type of instruction where we precise one opcode and three operand value. So just easy like that. Don't stress yourself. Good. So say exactly, be direct. Now let me just take example now for one address. So example of one address here, I can have something like this at maybe R1. Okay. This when you see something like that, just with one operand, because here the operation is what the opcode is just add. But what follows here are precise what one operand. And how it works, they can give this same question where they say C equals to A plus B, and they ask you to represent it, but now using the what address instruction, not 0 again. So to do so, the same reasoning. What happens here is, don't remove in mind that this one address is accumulator based. Accumulator based, how is it working? So the first thing here, accumulator based here simply means everything is being manipulated using the accumulator. And accumulator here, I'm talking about a register. I think everybody know it. Good. Accumulator here simply means, accumulator base here simply means any operation you want to do, you are manipulating a register. Meaning if you want to add something, make sure that you store it in the register first. You do your operation. You store it in the accumulator first. Sorry, you do your operation. Then the result is being stored back in the accumulator. So let me just do it. For example, I want to represent C equals to A plus B. So how to do so? So yeah, the first thing is I need to store A in the accumulator. So remember that A here is just an address location storing something. So here you use what? Load. Remember load helps you to move something from memory to register. So here I'm going to say load. Okay, load, what happened? You write here accumulator. Here you write A, something like that. Okay, you can write it like that. So here this instruction means that you are taking what is at the level of A, you put it where in the accumulator. The next thing here you just say add, you say R1. When you say add R1, what happens here is he's going to take the content of R1 plus the content of the accumulator, and this result is going to store it back in the accumulator. So this is what happens here. So you are seeing that when you say add R1, automatically he knows that the other operand value is in the accumulator, because when you have just one operand, it means that the other is in the accumulator. That's why we call it accumulator based, meaning that the accumulator is being manipulated here. Remember, the accumulator is a register. Good. Now the result is in the accumulator. So the next thing is what? You need to remove from this accumulator and store it where? And store in your memory what? C, at the location C. And to do so, yeah, you can use store. You can just say store what? You say store, you can even put C here. Then you put here, if you want you put it in square bracket here, it's not disturbing. Then you put arc here. Good. But now the next thing I wanted to precise, I'm even doing a small mistake, please. So generally when you are manipulating where's the eraser? When you are manipulating load and store, don't precise square bracket. Now why is that we don't precise square bracket here? Because we know already that load and store manipulates memory. So when you are precising square bracket like that, it's as if you are trying to access a memory location twice. Good. So that's why here you don't need to precise it. No, it's not necessary. Good. So when you're using load and store, you write A. A means you access the location of A, because you are manipulating load. The same thing when you say C and you are using the instruction store, C here simply means the location of C. Good. So let me just continue. Yeah, it's all. So this next instruction here means what happened with my pencil? So this next instruction here means what? It means that C take the content of what? Of the accumulator. So that's the meaning of that. Perfect. It's all. So this one address. Now for two address, so yeah, I'm not wasting time. For two address, example, I think I've explained two address already. Imagine now you have something like add R1, R2. So two address. Remember here we precise what? Two operand value. So this is being interpreted by doing what? This here simply means that you take R1 plus what? Plus R2, and this result is being stored back where? In R1. Please. The first thing that you see beside the operator here is where we are storing back. Now for three address, three address is very easy. Let me just take it somewhere here. For example, for three address, imagine I do something like add maybe R1, comma R2, comma R3. R3. Good. So yeah, this simply means that you are adding the content of R2 and R3 and you store it back in R1. So this is the same as saying that R1 is taking what? R2 plus R plus R3. Good. So what we did here is very, very important, but it's not all on the chapter. We move now to the next part, and after this now we just look some past questions. So you people see that computer science is not really easy like ICT that you can just brush it and pass very fast. There are certain concepts you must know, because by the time you don't know it, it becomes very easy to answer questions. Sometimes questions become even ambiguous to you people because we lack certain things. Okay, can we continue? Okay. We move. Wait, I think. Okay. Now, so we are done with type of instruction. Nice. Instruction format, correct. Okay. Now, the next thing I want to mention is, let me go back to that instruction format. Imagine that you have something like this, an instruction format. Let me just take a black pen. Imagine that you have an instruction format like this. And the question said that the opcode is represented using 3 bits. And that the operand is represented using maybe 4 bits. So the total size in fact of this instruction is 7 bits. Now, if the opcode here is storing 3 bits, if they ask you the total number of operations, in fact, your CPU can process, what will be the answer here? It's clear. The answer is 2 to the power n, so 2 to the power 3, which is what? 8. From here now you have for the total number, because remember at the level of the opcode here, each code will be represented using bits. Never forget that. So if they say 3 bits, it means that maybe the first code, let us say the first code is at. So it means that here at will be represented using what? 0. Let me just take any case here. 0, 1, 0. Because never forget again that the computer manipulates with binary numbers. So all what we are doing at the end, they are being converted back into binary before being processed. This is how digital devices work. Good. Now, so this is what happens here. The same thing. If they ask what is the total number of instruction we can access, or maybe the total number of data we can access, from here we know that the instruction that we can access in fact to manipulate, or the data that we can access to manipulate, is at the level of the operand. So the answer will be what? 2 to the power 4, which is what? 16. So this is when they ask for the total. But there's one thing I think with June 25 where they did not ask for the total, but they asked but for the highest address. So take note, when they say highest address, it simply means what? Because generally these addresses, remember that we are always starting at what? At 0. So it simply means what? That if I'm starting, let me just even take the case of this opcode. Imagine that they ask for the highest address to access an opcode. How are you going to do so? So yeah, the total is what? Is 8. Let me just try to enumerate. Let us say if I want to list all the options. How am I going to represent it? 0, 0, 0, 0, 1, 1, 1, 1. Okay. 0, 1, 0, 1, 0, 1, 0, 1. Okay. Then, oh, sorry. What am I doing like that? I hope I'm not tired. I'm trying to list all the options. Okay. 0, 0, 1, 1, 0, 0, 1, 1. Okay, 0, 1, 0, 1, 0, 1, 0, 1. So if you count this in total, you have how many? 1, 2, 3, 4, 5, 6, 7, 8. So this is the total. But now, if you look very well, the first address here, I think everybody in this group knows how to convert binary to decimal. The first address here is what? Is 0. The second is what? Is 1. The next is what? Is 2. And this last one is what? 1, 1, 1 is equivalent to what? Is equivalent to 7. So imagine that the question asks you for the highest address, not the total, the highest. In this case, the highest is not 8, no, but the highest is what? Is 7. Take note of that. And this is the trick with this June 25. Let me just go to the paper. This is where some students had problem with that June 25 question. Yes, June 25 question 1. Look at question 1. Question 1, they say a processor with a machine code instruction. So let us do it directly from what I've explained there. A processor with a machine code instruction of 16 bits, meaning that all this instruction is 16 bits. It uses 6 of this bit for the opcode. So everybody know the opcode. This first part here, opcode. You see how many? 6 bits. Okay. Now, and the remaining 10 bits for operand. Okay, operand. How many? 10 bits. Perfect. So you represent it like that so that you understand what you are doing. Now, the next thing they say, what is it? A. They say what is the highest? What is the highest memory address that can be addressed by an instruction? So remember that instruction is what is being stored in the memory. Take note of that. And here they're asking the highest memory address that can be addressed by an instruction. So since here an instruction is represented in how many bits? 10. Good. So the instruction here is like the data you'll be applying your operation on, because opcode here is the different operation you'll be using. The different operation will be interpreted by the CPU. So now here the total number normally is what? 2 to the power 10, which is 1024. But now if you try to, the interval is from 0 to 102.23. Good, because if you start at 0, it means that the last should be did. So it means that the answer here is 1023. Take note, not 1024. Now the B part, they say how many different opcodes can this processor have? So here they're asking the total number of opcode. They did not say the highest or the minimum, no. So the total number of opcode, I think, is clear. If one is represented using 6, meaning the total number is what? 2 to the power 6. The answer is what? 64, right? Good. 64 opcode in total. Good. So you are done with the B part. Now the C part, they say describe the code. We did it already. So you have seen that 2 marks. So the question, they are not difficult, but if you don't have this information, you cannot answer them. You cannot answer them. Good. Is it okay if you equally indicate? Okay.
So I have a question.
Yes, ask your question. Comfort.
So on the part, why, how do you have 1023?
Yes, in fact, are you understanding first of all how I'm having the total number of addresses to address each instruction?
Yes, sir.
2 to the power n, right? And it's exactly, you're asking how I'm having 1023. That is why before answering this question, I told this example that imagine that here they are asking for the highest address to access an opcode. Here, if the number of bits for a single opcode is 3, the highest is given, the total is given by what first? The total is 2 to the power, which is what? 8, you see. And if the total is 8, if you start at 0 and you want to reach 8, the last should be what? 7. You see, just I don't want to say it like that. That is why I've decided to take this in fact so that I'm proving to you what I'm saying. From here, if I'm enumerating all the different combinations of 3 bits, is it here? Now try to convert this first combination. You see that is 0. Come and convert the last one. If you convert 111, do you know how to convert binary to decimal?
Yes, sir.
Good. If you convert 111, the answer is what? Is 7, right? Good. So, and it's the same thing. It's the same thing with this June 2025. Just for June 2025, it's not saying you need to enumerate all the combinations to see that the last one is the number 1023. No. If the total here is 1024, it simply means that seeing the first is 0, the last should be what? Just remove 1 now.
1023.
And that should be what? The highest, right?
Yes, sir.
Exactly. Is it okay now?
Yes, sir. Thank you, sir.
Good. If they ask now for the smallest should be 0. They ask the second is 1, and so on and so forth. But they will never ask you the full number of bits. No, it's not possible, because imagine that you want to enumerate all the combination of 10 bits. It's too long, because 2 to the power 10 is what? 1024. 1024 divided by 2 is what? Is something like, I don't know, 512. So you align 512 0, 512 1, you go to the next. You cannot do that in the exam. But you can just ask that type of question if maybe it's 3 bits, like what I took for this example here. 3 bits. Yeah, I see that with 3 bits I can really enumerate everything, right? Good. But for with that one, you cannot really ask that. I hope you are okay. Are you okay?
Yes, sir.
Okay. We go to the next part. So what we did here is help me also answer 2025, but it's not all. There are other type of questions under this. So let us continue there. What's even the time? Wow. After this last part, I think I will stop here. At least you have learned so many things. And next time we'll program something else. Now, the next thing you need to know is what we call addressing mode. This one is not optional. You must know it. You must know it. Addressing mode. Now, before talking about addressing mode, let me just explain how we are introducing this, in fact, into this chapter. Now, what happened is, if I take my instruction like this, imagine that the operand is represented using 3-bit, no problem. The opcode, and then the operand here is represented using 4 bits. Imagine that I have something like this to execute, maybe at, let us say 7. Okay, at 7, what happens? Let us say this at here is coded using 3-bit. Maybe let me just take an example, 0 1 0. Let me just say that, okay, this is the code for this one. Now, code 7. What is 7 in binary? 7 in binary is 1 1 1. Now, and 1 1 1 into 4-bit, it means that you just add 0 to the left. So it means that here you can just put 0 1 1 1. Perfect. So you are seeing that for you to represent this, in fact, there's no problem. You can store the value 7 directly into your instruction. But imagine that I want to do something like this at, maybe, I don't know, something like 33. Now, at, okay, this is the code of at here. Now, convert 33 to binary. If I use this method, 1 2 4 8 16 32. So 33 is the same as what? 33 is the same as 32 plus 1. Yeah, I off this, I off this, I off this. So 33 here is the same as what? 1 0 0 0 0 1 base 2. So here you can use with long division method. So if you don't know this method, there's no problem. Do your normal long division, you still have the answer. So it means that here 32 is represented using what? It's represented using 1 2 3 4 5 6 bits. But what happens here is we have only how many bits? Only 4 bits. So it's here. So you are saying that this 36 cannot be stored here. So the solution now to handle this is to store the 36 bit in the memory. In the memory. Yeah, I'm talking about RAM. So here, this is my memory here. And in this memory, I'm going to store this my number. The number is what? 1 0 0 0 0 1. And now this, what I'm storing here is at a particular address. Let us say the address is maybe 1 1. See the address here, 1 1. Good. Now, if the address is 1 1, it simply means that at the level of the instruction, let me just use an eraser. It means that at the level of the instruction, I'm no more storing the value directly, but I'm storing what? I'm storing now the address. The address is what? 1 1. And this address, you must also code it to 4 bits. So you just put 0 0 here. So here you're not storing the address to access what? To access your data. So this is what happens here. But now, small problem. The problem here is when the CPU will receive this instruction, for him to execute it, he's going to ask himself that, okay. He's going to ask himself that, okay. At the level of the operand, is it an address that is here or the actual value? So now the question you're asking yourself is, how will the CPU distinguish that this operand field is storing but the actual data, or storing but the address, maybe location, or I don't know, of where the actual data is being stored? Now, for us to handle this situation, in the instruction, we are going to add another field called the addressing mode. Now, imagine that maybe my addressing mode is coded using 1 bit, and let us say the opcode is 3 bit, and maybe the opcode is 3 bit, yes, and the operand is also 3 bit. It means that here I'm going to have my 0 1 0. Here I'm going to have what? 0 1 1, meaning the address of this. And here, now if the addressing mode is coded in 1 bit, what are the different possibilities? The different combination of 1 bit. It's only 0 or 1. Now, so in this case now, it depends on how you are constructing the architecture. The person constructing and can say, okay, when you see 0, 0 means that what follows here at the level of the operand field is the address of a location where you have the actual value to manipulate. Another person now, you can be doing his architecture now and say that, okay, when you see by this 1, so this is the meaning of 0. Another person can say that, okay, when here you have but 1 here means that, okay, that what you are having here is the actual data, but not the address location of where you are supposed to find the data. So coming to this, in fact, addressing mode is simply used to indicate where to find the operand value on which we are supposed to perform an operation. That is the use of the addressing mode. It's indicating the location of operand value on which we are supposed to perform operation. get it like that. It's very, very interesting, and I think I'm clear with that. Now, so I've explained addressing mode, and there are past questions where they're asking different addressing mode, things like that. Just that it's not all concerning addressing mode. The next type of question you see under addressing mode is what? Is type of addressing mode. Types of addressing mode. So this is where we will conclude this class. With type of addressing mode, we answer a question and we end here. And after this, I think we have even covered everything here. Yeah, we covered everything. So now it's for you to maybe answer other questions. You have difficulty, you bring it. You cannot really answer everything. We don't have time. Now, type of addressing mode. Okay. Now, concerning the type of addressing mode, the first one here is what we call immediate addressing mode. Now, so immediate addressing mode, in fact, I will just explain, but draw some diagram for illustration. I think with that you understand it better. Let me just increase this. So immediate addressing mode is a type of addressing mode where the operand field contain, or let me just say it's a type of addressing mode where the operand value is stored directly in the instruction. Good. Meaning that the operand value here is not stored in a particular memory. No, it is stored directly in the instruction. And this is how the things work. So this is my instruction here. Good. So here this is my opcode, and here this is my operand value. So it is directly in the instruction. And how is it represented? It is represented using hashtag, meaning e.g. It simply means that if I have something like this, if they give you this instruction, add maybe, I don't know, R1, maybe hashtag 5. Good. So by the time you see this type of thing, especially paper 1, and they ask which type of addressing mode is yours here, the answer is what? Immediate addressing mode. So when you see hashtag, hashtag is meaning that this file is stored directly in the instruction. This file is not stored in a particular memory or register. No, it is being stored directly where? In the instruction. Good. Take note of that. And I think you know how to represent it, right? This means what? This means that you are doing R1 plus 5, and this result is being stored where? In R1. So this example of immediate. Now we go to the next thing. The next one is what we call direct, or we call it absolute addressing mode. Direct or absolute addressing mode. So now, so this is a type of addressing mode where the operand field, when I'm talking about the operand field, I think everybody's understanding it. The operand field store the address of the operand value. And this address of the operand value is also known as, in fact, is always known as effective address. Effective address. Effective, like this. Good. Now let me just draw it for you to get it well. So this is my instruction here. Instruction. Okay. So here you have your operand code normally. Now at the level of the operand field, you're not having the operand value here, no, but you have what? The effective address. And this effective address now is what? Is the address. This is my memory here. So this is your memory here. And don't draw memory here. This is your memory. And it's inside this your memory that you are having now your operand value. And that operand value is at the address EA. Like this. So this is what we call direct, or we call it what? Absolute addressing mode. So with absolute or direct addressing mode, master the two names, because in the exam they like to interchange it. Good. So here what happened? The operand field stores the effective address of the operand value. Take note of that. Good. And I think the difference between this and immediate is clear. It's clear. Good. Immediate, he's storing, but directly he directly store the value here. You see. Now, and how to represent direct or absolute addressing mode? Generally, it is represented using this symbol here, this arrow bars, or sometimes it's represented using square bracket. In majority of the time, you even see square bracket. Good. So, e.g., in mind that if I say something like add, maybe I don't know, R1, and I put maybe something like that, maybe I don't know, 5, something here. Good. So don't go and say that this is the same as R1 plus 5 is taking the content of R1. 0. Because here, this 5 here is not the actual data you are manipulating. No. But this 5 here represent what? An address location. Good. Because this 5 here, when you see the square bracket, it means that you are at the level of absolute addressing mode. Meaning that the instruction itself, that operand field is storing but an address, and that address is 5. Now at the location 5, you have now the real content that you are supposed to add. So if you want to rewrite this operation, make sure you rewrite it, and this 5 you just maintain his square bracket here. Don't remove it, and now it's okay. Nice. So this is for direct or absolute. And I think June 2020, there are questions, we are coming there. June 2024, 23, something like that. Yeah, they are asking question. Like remember, it's a question they have define direct addressing mode. Define direct or absolute. I think it's even June 25, something like June 24, 24. You see there. Now we go to the next one, number 3. So we are done with direct addressing mode. Number 3 here is what we call indirect addressing mode. So how is indirect addressing mode working? It's very easy. Indirect addressing mode is a type of addressing mode where the operand field stores the address of the effective, or let me just try to reformulate it, please, because this one you need to concentrate to get it. Indirect addressing mode, it's a type of, or let me just even draw it, yeah, so that when I'm explaining, everybody is following, because if I just say it like that, since people are tired, you will not get it well. So yeah, opcode is not having a problem. So yeah, now I'm having an address. Okay, here I have my memory like this. RAM. Okay, so yeah, I'm having a location. Let us say this address here is maybe called A. Okay, so this location here is A, and this A is having the effective address. Draw something like that. Now I have another location here. This location have now the operand value. So and this here is EA. Good. So the first thing you realize here is that we are accessing the memory twice. So how to define this is very easy. Indirect addressing mode is a type of addressing mode where the operand field stores the address of the effective address where the operand value is stored. It's clear. So yeah, the operand field is not having the effective address, no, but it's having an address, and that address location we have the effective address, and from the effective address now we can access the operand value. So here in indirect addressing mode, we access the memory twice. Don't forget that. So the operand field contains the address of the effective address, which contains the operand value. So it's the effective. So never forget that when you see effective address is always that final address that contains the operand value. That's why you're seeing like this other address, I'm just calling it A. Hope you are clear there. And it's all. Now the next one, I'm not wasting time there because it's similar. Number 4 here is what we call register addressing mode. So in register addressing mode, what happens here is the operand are registers. It's all. So the operand field are registers. Now we go to number 5. Number 5 here is what we call indirect register addressing mode. Now under indirect register addressing mode is the same thing like this indirect addressing mode. Just that what happens here is, remember in register addressing mode you have something like this. Here is the opcode here. And this operand field is what? Is a register. Now when you say indirect register addressing mode, it simply means that you still have something like this where you have the opcode like this. Here you have the register, but this register is no more storing the operand value directly, because up here the register is storing the operand value, but here now the register is storing by the effective address of the memory location RAM. And this arrow also, please, is a mistake, of the memory location. This is EA, the memory location where you have the actual operand value. So this all. It's all. So we are done with this one. With this one. Now they go to the last one. The last one now will help us to answer a question, because I don't like to do things halfway. So let us go to the last one. People should just support. This is the last one. Number 6. The last one is what we call index addressing. I don't know who is joining there. Who is joining at this time like this? Julien Docmo, you have missed a lot. So yes, I'm recording the tutorial, so don't worry, you people can watch it back online and so on and so forth. So just make sure you share it to others. I think this tutorial will really help others. So let us finish first before we discuss. Now, index addressing mode. Now at the level of index addressing mode, generally this is used for the manipulation of arrays. Now let me explain how it works. what happens here is the effective address is being constructed here. And how are we constructing this effective address? Because the other one, effective address, are just normal addresses, very easy. But with index addressing mode, generally effective address is being constructed by doing what? By taking the base address plus what we call the offset, or it is also called displacement. So this is the formula of effective address when you are at the level of index addressing mode. And how is it working? Let me just show you how it's working, because we are going to use this now for equation. Okay, now the first thing, generally this is used to manipulate arrays. Let me just draw an array here. I think with this array the explanation will be very easy. Let me just draw an array. Generally this array is represented something like this with location, and each location is being accessed with an index, so 0, 1, 2, 3, and so on and so forth. So the first thing I want you to know, let us say this array is called maybe A. When I say something like A of 0, what is the meaning of A of 0? A of 0 simply means that you are trying to access what? The first location of your array. So this first location of the array, please never forget, is what we call the base address. So this A of 0 represents in fact the address location of this first element here. Let us say the element here is maybe, I don't know, let us say 1, 2, 3, and 4. And this A of 0 is the same thing as saying A. A of 0 and A are the same thing. A of 0, or you say A, the base address of the first location. It's always like that. So yeah, we are not. It's true that this is a thing that I like to prove it when I'm doing programming with my student, but since practical is over, I don't want to insist here. But just know that A of 0 represents what? The base address. And how to obtain now, how to access the next location of your array is just by taking what? The base address plus a particular index. That is why you are seeing that the next element here is being accessed at what? At 0 plus 1. You take 0 plus 1, it's going to make what? A of 1. And A of 1 here is what? It's already the second location. So this is how we work it. And it's the same thing what happens here. So when I say effective address here simply means what? My base address here is what? Is A of 0, or let me just say 0, something like that. No, let me just say A of 0. Yeah, A of 0 plus, now the offset here simply represent the index. But just that offset is not just index like that. No, generally offset is having a formula. Let me just write it here. Offset is given by index times size of array element. Take this very seriously, because question, they are precising this, and if you are not focusing very well, you go and take offset as index. No, index here is what? Size. Offset here is what? Size time, and index time size of array element. But generally we are just doing plus the index, because by default the size of each element here is 1 byte, and 1 times the index is still that number itself. That's why we are always incrementing just like that. We say A1, A2, A3, A4, A of 4, A of 5, and so on and so forth. You see, because we consider that each element in that array location is 1 byte, and 1 time index is still the index itself. But I'm saying it here because there are some questions where they can ask you to, I don't know, use indexing addressing mode to do this and do that, and they say consider each element to have the size this. By the time they mention that, make sure that you take that size, you multiply by the index before using it in fact. So after knowing this, now it's okay. So we go now to the next part, which is how to represent this. Generally, this is how the thing is represented. So this is how the thing is represented. And yeah, someone did not even ask this question, because yeah, I'll show you how to represent immediate with hashtag, direct with this square bracket. Now, generally, index addressing mode is represented using 2 square brackets like this. I think everybody knows the meaning of 2 square brackets. Because remember that in indirect, what am I saying? Index. Generally, I was talking about indirect, sorry. Generally, indirect addressing mode is represented using 2 square brackets. Why? Because here we access the memory twice. So the first time that you access the first memory with this square bracket is to access the effective address. Now the second time that is to access the content that is found at the level of the effective address. That's why for indirect addressing mode you see this. Now for register there is no problem. Generally here you just use a normal R. You see R1, R2, R3, things like that. So this register addressing mode, we use normal R. Now indirect register addressing mode, here you are using R now. Just that in R now you are using square bracket. So like saying content of R. Take note of that. Seeing the content of R here in indirect addressing mode is an address. So putting just one square saying that okay, at that address now we fetch what is at that location in the memory. So take note of things like that. Now the next thing is how to represent things at the level of index addressing mode. So it's very easy. Generally, index addressing mode is being represented using a square bracket, and this square bracket contain, let me just clean something. This square bracket contain what? Contain your base. Base is having one S. Contain your base address plus offset. Go. So this is what happens here. Now let us go and answer question June 25. And June 25, we are using this index addressing mode and so on and so forth. So you see how to use it. Take note of that. So June 20, I don't know what is June 25. I think it's June 23. Yeah, this one nice question I want us to answer. June 20. I think it's June 23. Let me just try to check that question. No, is it June 24?
23, question 2.
June 23.
Yes, question 2.
June 23. Yes, we are coming to June 23 question 2. I want us to answer a question under this index addressing mode first. We are coming there. Maybe June 24 that question. I don't know. Yeah, it's June 24. So before answering that 2023, let us answer June 24. A very nice question. Under what I'm just from explaining under index addressing mode, so that you understand how to use it. Now let us read this question. They say, consider the following assignment statement written in high level language, where A is an array, comma, equals to the assignment operator and array indexing start with 0. This information is very important. Array indexing start with 0. When you say array indexing start with 0, it simply means that your base address should be what? A of 0. Take note of that. Now we continue. So this is what they are giving us. They are giving this to us. They say A of 3 is equal to A of 2 plus A of 1. Question 1, or let me say A, they say explain what is meant by addressing mode. We did that already. So no stress. So addressing mode in fact is a way of showing the location of the operand value on which an operation will be performed on. It's all. So it's just a way in fact to show the location of the operand value. It's all. Good. On which operation will be performed on. The next thing that they say, what is absolute addressing? So absolute addressing here is the same thing as asking what is direct addressing. And you know this is just a type of addressing mode where the operand field contains what? The effective address of the operand value. And it's all. You have your 2 marks. B. They say, okay, now B is the most important part. How many marks? 4. They say using register and index addressing modes only. Using register and index addressing mode only, comma, show how. So the first thing I want you to know there is they are saying that you should use register and indexing addressing mode. So you are seeing that there are some questions, and it's like that. There are some questions where they are mixing 2 addressing modes at the same time. But yeah, the general idea remains the same. This part where they say register here simply means that you'll be manipulating register. Manipulating register simply means that before doing an operation, make sure you store your value in a register first before you do that operation. Like here, these are arrays here. You are seeing that A of 2 here is just the address of a location. Just that what is found at this location, you will take that value, you put in a register first before doing this addition. So that is why they say register, that we should use register. Now indexing addressing mode here is just showing us how we are supposed to access a data. Because generally to access something in an array is what? Is A of something, A of an index here. Just that in indexing addressing mode, what is inside here generally is an address. And that address in this case is what? Effective address, which is given by what? Which is given by base address plus offset. So the idea is just to calculate this effective address so that you'll be using something like A of what? Of effective address. Good. Then we are coming to that, so don't worry. Let me just clean this to avoid any confusion. Good. We continue. So you know the addressing mode to use. Now they say show how you will implement the above statement in assembly. Okay. They say assume that the base address of array A is stored in a register R0. As I was telling you, dude. That here all what we are doing, we must store it somewhere in register because it's a register. So, and this question is already telling you that R0 here is what? Your base what? Base address. So always take your data first. Base address. So this is the first relevant information we are having. The second, because the first one was using register indexing. Okay, so yes, I'm done with this instruction. Now they say each element occupies a single byte. This instruction here also is very, very interesting. Each element occupies a single byte. It means that in your array, each element here is a single byte. And where is this information going to help you? It's going to help you on how to calculate the offset. Offset normally is index times size of array element. You remember this. But since the size is one byte, they say a single byte, it simply means that by default your offset is what? Is index, because one time the index here is means what? Is one time index is still the index, you see. So just to tell you that, and from this instruction, where are the index? Yeah, when you say a of 1, that 1 represents an index. A of 2, that 2 represents an index. A of 3, that 3 represents an index. And since the size is 1, it simply means that this value here, you are not multiplying them. You will leave it like that. So when you have this 1, you leave the 1 like that. You leave the 2 like that, the 3 like that. So this is the first thing you're supposed to know. But let us continue first. So this is the relevant information. Now, continuation, they say, and other registers are named R1, R2, R3. So here now, remember that you are at the level of register addressing mode. So anything must be stored first in the register. And since R0 is representing a base address, it means that don't use it again. When you are using your register, start using it from R1, R2, Rn. It depends on you, the number of registers you'll be using. There, they don't impose anything, you are free. Okay. Rn for some positive integer n. So you're understanding this. Now they say, explain any other notation you use in your answer. Good. So now let us do this question together. It's very easy. So step number 1, here we are conscious that you are supposed to load everything into register. So this is my instruction here. The first thing here, I'm going to say R1. Oh, sorry. I'm supposed to load. So here I will say load what? I'm supposed to load something into the register. But now what I'm loading, this I'm going to access that value. To access here, since we are using indexing addressing mode, I'm going to put my square bracket, and my base address is what? R0. R0 plus the index here is what? Here is the offset, sorry. But the offset here, seeing the offset here is equals to index times size of memory, size of array element, and array element is 1 byte. So it means that here you're just putting the index. Now, the first thing here is I want to load, let me just bring it. I want to load this A1 into the memory. I mean that the content of this A1, sorry, I want to load it in a register R1. So here, the index here for A1 is what? Is 1. So you just come and write 1 here. Good. So this instruction means what? This instruction means that you are taking the content of array of 1 and you are storing it into R1. This is what you are doing. You have to access array of 1, seeing it is index addressing mode. And I said there in the note that indexing addressing mode, you put your square bracket, you always put your base address plus what? Plus the offset. And the offset in this our own case, just the index. Perfect. Now I'm done there. The next thing is what I load also what is on in A2. So yeah, I'm going to say load. I use a register called R2. And here I'm just going to say R0, which is the base address plus the offset. The offset here is what? Is so we are not doing any multiplication. So here this instruction means what? That take the content of A of 2 and store it in R2. So now since my two registers are already having the content, the next thing is so I can just use my operation at what? R1, R2. What is at R1, R2 doing? I'm not more having speed. Let me just continue down here. I think people are seeing. Yeah, this man is doing what? This man here is doing something like this. He's taking R1 plus R2, and this content is being stored where? In R1. So this is what the man is doing. But also, we want the content to be stored where? In array of 3. You see? So it means that here now I need to use what? Array of 3. I need to use store. So that store will take something from register to memory. I think you remember that. So here I'm going to say store. Now here you precise how to access the memory of A3 here. You just say here R0, your base address plus what? Plus 3. And here you write what? You write R1. So knowing that the result of this addition will be stored in R1. Now store here simply means that take what is inside R1 and store it where? So let me just comment it here. This means that array of 3 is taking R1. So this is the meaning of this part in fact. And it's all. So this is what they're asking you. This is your assembly code here. Your assembly code is this for instruction 1, 2, 3, and 4. You have all your marks. You have different way of doing it, but this is just the simplest way I'm representing. So I repeat again, that register that they precise in the question, they say using register is just for you to understand that you must load your thing in register first before manipulating. Good. Because if the question did not precise using register, in that case you don't even need to use load again. No. In that case you just go directly and say add. You take this one here. If they say using index only, let me just do it somewhere here. You just come and say add what? You say add here R0 plus 1, okay, comma R0 plus 2. You see, meaning that you manipulate the memory directly. You do your operation, you store without storing it in a particular register before, things like that. But since they don't want you to manipulate it like that, that is why they precise using register, knowing that you take from memory, you store it first. Good. And here now they want you to take from memory using index addressing mode, meaning that you are just taking from memory using this representation, what I'm doing here, because this all for register addressing mode. You have different way of representing index addressing mode. So I wanted to say index addressing mode. You have different way of representing index addressing mode, but this is the simplest method here, by putting your square bracket, knowing that in the square bracket you put your base address. Always put your base address plus your index plus your offset, please. I always like to say offset, because when I say index here, it's as if I'm neglecting that part where they can precise the size of element of the array. So that is why I'm always saying offset, so that if the size is 1, then okay, you use your index normally there, and you access your element, you do what you're supposed to do. Okay, I think I'm clear. But now on your own part, I need to be sure, is it okay? If it's okay, leave comment, leave a like, leave a comment. Let me confirm. Comfort merit, perfect. What about the others? Yes, we are done like this, but I need confirmation. If you're understanding, if everything is clear, you indicate. Emmanuel, yes, okay. Let me just check the others. What about the others? Others are just staying quiet. Gainiform Precious, is it okay? Comfort merit, yes, she replied already. Raim, is Raim still there? I don't know. Emmanuel, I'm waiting a reply from you people. Wilfried, yeah, Julien Docmo, fine. Yeah, because I'm really trying to simplify this concept that sometimes look difficult for some students. Okay, if you people got it, very nice. Oof, I'm tired. I think we can end here. Is it okay? Can we end here? I think we did really something very interesting. Okay. Yes, so today we really covered something very interesting. And all the different chapters in computer science play, they are like this. There's nothing behind. You just need to have good explanation behind it and answer more questions. It's all. So like as what we did now under computer architecture, go and answer more questions, because it made me sure I'm tired. Even this 2023, this question here, a RISC processor has state, it's very easy. So people should try it first. You see in the group now. Yes, I will try to help you, and yes, I will even answer it for you. There's nothing there. You just read the question very well, you represent. Good. So I'll be waiting your reply. Any problem, I want to be aware of your problem. If there is no problem, good, we just leave it like that. Even this Roman 3, yes, to single instruction, single data, so draw this, there's nothing. So we try to do it, so that now the next online class, let me just start by doing correction of all these small things, and let me start by doing this small correction before we even start with a new chapter. Comfort say yes, I understood a lot of things. I was confused. Yes, okay. Yes, all the different chapters, like even logic gate. Sometimes see students crying about half others, full other. There's nothing there. So I think that one, even in 20 minutes, I can really explain everything. So under algorithms also, yeah. For algorithm, I cannot really explain everything. So the thing you have is the small level there. So let me just try to explain something like functions, recursive function, iterative function, because these are the type of thing you need to know. Your question is centered around them. Now the next thing also, you just need to know how searching algorithm works. Someone is talking about Boolean algebra. Yes, we discussed that. It's under logic gate. We are going to discuss about that. Now, searching algorithm. Searching algorithm, you don't need to know the algorithm, no. You just need to know the working principle. It's all. It's all. So that one also you need to know it under algorithm. You need to know recursive function, iterative function. Clear, because they are always asking this type of question where they are comparing both iterative and recursive. So that's what I'm saying. Answer more questions to be aware of the type of thing they ask in the exam. And the next thing is yeah. So if you are studying algorithm, you are focusing on these things. In fact, the next thing under algorithm also is data structure part. Very important. Binary, tree, traversal, all these things. Post order, pre order. In fact, there's nothing there also. So we can take another class for that. So I'm trying to see, maybe we will have again two classes together. Two classes. One maybe for general things and maybe another one just for algorithm, data structure, and it's all. We don't have enough time. I need to work with the ICT also. But as you are working, any problem, please just indicate. Just indicate. My aim is that people should pass and pass very well. Yes, that at least when you're in the exam hall, you're not just in front of your paper frustrated like that. Think that it's true that you are not really working since the beginning. In fact, yes, I think amongst you there are some of my students that we are working together in New Century, and I don't know if there's any student from Pianju because these are my schools there where I'm teaching, New Century and Pianju, and also Jenny student, yeah, in some centers. So okay, nice. So it's a little bit that, so we are going to end here for today. So you people should prepare well and pass because we are counting on you people. After now, your GC, there's another part, so entering into professional school, things like that, and so on and so forth. And school 4 is having another section, in fact, which is the confidence cooperation. So the aim of confidence cooperation is to guide you people to at the level of career orientation, how to prepare, in fact, for concours, because there are some prestigious schools here in Yaoundé, Douala, Boya, in fact, in Cameroon, that to enter you need to pass through a concours. So confidence cooperation is preparing you for that. So any information concerning this type of thing, just contact me and we discuss directly. Okay, so thank you very much and see you. So I think yes, I've restarted the tutorial. It's 2 hours 40 minutes this tutorial. I don't know how I'm going to upload it. Maybe I will just divide it into different sessions because some students are very lazy to see long videos like this. Okay, anyhow. So goodbye. So just leave a like before leaving. Okay. See you. And the next step, please, in the group, I'm waiting, or even you can just DM me directly. Send me a screen capture of the result you had for June 25 online exam, because I need to be sure that you are really answering that MCQ question, because sometimes people don't understand the importance of it. So please do so, because if you do that for 2025, you do for 2024 also. And when you are doing it, after answering all the MCQ questions, you go back again, you re-answer, you go through the correction, because the way the correction are details there. This is something that you will discover. Some students have started it already, so you also discover. Because my aim is that if you do that for 2025, 2024, it's going to encourage me to upload 2023, because it's taking time. Because at least paper 1, if you are able to do like this for just 4 pass year, 3 pass year, it's okay for the exam. But if you don't do so, you enter into the exam and I'm telling you, all your questions, you just be closing your eyes and take, because you don't know. Take note of that. So everything is preparation. Okay, so I'm ending here. Flying taxonomy and so on. Okay, yes. Next class, just recall it. So that let me just try to touch some certain things there before we go to the next chapter. Even here, yeah, I just need to mention some few things to clear your doubt. Okay, so bye bye.